In this video, I'm going to be explaining choice of basis and how this relates to measurements on a quantum computer. So I'm going to start with the definition of a basis. So this is taken from Wikipedia, and this is a pretty rigorous definition, but it's helpful. A basis B of a vector space V over a field F, so F might be like the complex numbers, is a linearly independent subset of V that spans V. So formally, what does that mean, right? So this basis is linearly independent. So for any subset of basis vectors in this basis and any choice of coefficients in that field, a linear combination of these vectors equating 0 forces these coefficients to be 0. And spanning, so the basis has to span the space, meaning that for any vector v in this vector space, there exist coefficients c1 through cn and vectors basis vectors v1 through vn, such that v is a linear combination of these basis vectors. So essentially, just any vector in the space can be represented as a linear combination of these basis vectors. And basis B is orthonormal if and only if for any two vectors in this basis, their inner product or dot product, right, if we're talking about 3 dimensions, is 0. And for any vector in this basis, the vector's norm is 1. So recall that the quantum state representing a single qubit, ket psi, can be written in the computational basis, right, which is this set ket 0 and ket 1, i.e. the z basis, as, alpha ket 0 plus beta ket 1, right? We've seen this a million times now. And so the mod square alpha, right, is the probability that you measure 0, and then the state collapses to ket 0. The mod square beta is the probability that you measure a 1, and then the state collapses to ket 1. But expressing ket psi in this basis is completely arbitrary, and we could just as easily express ket psi in the Hadamard basis, for example, which are ket plus and ket minus, where ket plus is this, equal superposition of 0 and 1, and ket minus is this superposition of 0 and 1 with this minus sign here. And so then if we want to rewrite ket 0 and ket 1 in terms of ket plus and ket minus, right, we can go ahead and add ket plus and ket minus and then just carry out all this algebra here. And what you'll see is that ket 0 is equal to ket plus ket minus over root 2, and ket 1 is ket plus minus ket minus over root 2. So we can then just plug these into the original state that we had written in the computational basis. So we go ahead and swap, right, what we just derived here, plugging in these new equations that we have. And then we just distribute and group like terms. And so we now see that the same quantum state, right, which was written in the computational basis, is now written in the Hadamard basis. And you can see, right, so it's written in these new vectors now, in terms of those new vectors, and the new amplitudes, right, are these coefficients here. And so these relationships are fixed, right, these equations here. And that's just from, right, like this basic algebra that we just showed up here. And so when we have a state in the z basis, and so when I say the z basis, right, the z basis is literally the set containing ket 0 and ket 1. And then canonically, right, we just say that the z basis is the computational basis. But we can just as easily say that the computational basis is the Hadamard basis, right? It's just completely arbitrary. But if we have a state in the z basis, right, so written in terms of ket 0 and ket 1, and we rewrite it in the Hadamard basis, which we just did above, right, to get this state. This step is just pure algebra, right? These states are the exact same physical state. We just re-express them differently. And so now, the mod square of this coefficient is going to be the probability that we measure, plus, and then the state collapses to ket plus, and then the mod square of this coefficient is going to be the probability that we measure minus, and then the state collapses to ket minus. And just for the sake of completeness, we typically, our hardware is typically suited to measure in one basis. So typically the z basis, right? So when I say measure plus, measure minus, that doesn't really make much sense, right? What we would usually do is we would apply, if you wanted to quote unquote measure in the Hadamard basis, we would apply a Hadamard gate to whatever state we were working in, and then we would measure in the z basis. And then what you would see is that you would get 0 with the same probability that you would have with the same probability here, and you would measure 1 with the same probability here. That's not really important to know, but it just seems kind of wonky when you say measure plus, measure minus, right? Like, what does that mean? That's just what I was saying there. And so again, right, it's also simply convention that we define and fix ket 0 to be the vector 1, 0, and ket 1 to be the vector 0, 1. So that is, we choose to work in the computational basis. And we really could equally define ket plus to be 1, 0, and ket minus to be 0 and 1. And then our computational basis would be the Hadamard basis instead of the z basis. But, it's just canonically, we just choose the z basis to be the computational basis. So, don't get confused, right? So there's two different things. There's the act of picking a basis to work in, so fixing your coordinates by defining or labeling which basis vectors you're going to define as your computational basis. And then there's just re-expressing your quantum state in a different basis using algebra, which is what we did up here. And you would only pick like this basis to work in at the very beginning of whatever, work you were doing. You would just fix it once. You would never revisit that ever again. But, you're probably going to be constantly switching between different bases. So it's good to make that distinction. And measuring with respect to a basis just means rewriting the quantum state in terms of that basis's orthonormal basis vectors. So for example, if we have a orthonormal basis with ket A and ket B, right, they're just completely arbitrary, then we can just rewrite ket psi using algebra in terms of ket A and ket B. And then if we measure with respect to this arbitrary basis, right, that just means that the mod A squared, right, this coefficient, is going to be the probability that we measure A, and then the state psi collapses to ket A. The mod square B is going to be the probability that we measure B, and then our state collapses to ket B. So I hope that this was helpful in distinguishing between, the different bases that we have, choosing different bases, changing between bases. A lot of this choice of basis stuff can be really confusing at first. It still confuses me to this day. So, like defining what computational basis actually is the fact that it's just totally completely arbitrary, right? So it's good to just nail that and drill that in early because it will save you a lot of pain and suffering down the road. I hope this was helpful, and thank you.